this semester, and I'm going to be doing a comprehensive final exam review for if you're in Chan's class, Bahal's class, or Fahim's class. This should cover most of the topics you guys will see on your final. Kind of like the agenda that I have set up is we're going to do like some warm-up questions like KVL, KCL, Ohm's law. Then we're going to get into like Thevenin and phasors. So just like how you did Thevenin way back in the beginning of the semester, now we're going to do them with phasors. Average and reactive power, we're going to go over a little bit on that. I don't expect it to be like a big portion of your exam, but definitely expect to see one reactive or average power question. An RL circuit, just to like for natural response dependent sources. RLC, and at the end I'm going to go over op-amp question. I know Chan's class doesn't do op-amps, but you do them in networks and systems, so it's like a good preview of that. Any questions before I get started? Okay. Let's see. Is the good? Yeah, move this. Okay. So this first question should take like 3 minutes. You want to find Vx, you want to find Ix, and you want to find I and V. As you notice, these two resistors are in series, right? So you can do, and they're in series with a voltage source. So you could just do a voltage division on that. But also notice that the polarity is switched. So when you find Vx, you're going to put a negative out front because of that polarity. So then this voltage source is 5 volts. The resistor you're looking at, the voltage you want, is 2. And then over the sum. So if there's a third resistor, you'd add that in there too. So 2 plus 1. And then that should be negative 10/3 volt. Same with Ix. You notice that there is a current source. So these aren't in parallel with 5, but if you add them up, they're in series, right? So they'll be in parallel with the 5, which is in parallel with the current source. So you could do a current division, right? But also notice that the current is going down. So naturally, it would want to split upwards. But this Ix is labeled going this way. So likewise, you're going to want to put, I'm going to write it. You want to put a negative out front. And then it's not the resistors that you want the current, not the branch of the resistors you want, but it's the opposite. So 2 amps over 5 ohms over all these 3 added. So 3 plus 1 plus 5, and that should equal a really bad number. Ix equals negative 5 over 504 amps. And now what about this one? Yeah, you have a question?
Is there any way you can explain the configuration of the current division?
Yeah. So current division, usually when you see it, it's a current source going up with 2 resistors in parallel. And these kind of naturally, it goes up and it splits downwards. So you do the current division the regular way. You'd have this resistor over these 2 added, and it would be positive, right? But here, the current is going down, and it's supposed to split upwards. But this Ix is labeled the opposite way. So that's where the negative comes in. Yeah, so if I had labeled Ix going up, it would be a positive. That kind of.
And the resistors always have to be in parallel.
Yes. So these weren't in parallel until you add them. So if I wanted to find this branch, it would be 4 over all these added. And then, erase this. And if you missed something, I mean, this is live streamed and recorded. You can check later on how I went over it. So now what about I and V? Can someone tell me right away what those values are?
For Ix, you got negative 5 over 5.
Yes. Did you get something else?
10 over 9.
10. So what did you, what was your current division for this?
I just, like, for the multiplication right there, 2 times 5 is 10 over 9.
Did I? Oh, my bad. So, see, this can trip you up on an exam. move it. Okay. This is 1,000 ohms. Everything else is in ohms, so my bad. This is actually 3 plus 1,000 plus 5, yeah. So that'll give you the, sorry, the negative 5 over 4, because this is the only one, they're all in amps, volts, and ohms, so you want to convert this one to ohms, so you can get it into amps. Good? Yeah, my bad. So someone said this goes to 0, right? Because there's a short. You see that? So if I were to add these two in parallel, and then add these two in series, they'd be directly in parallel with the short. So this value would go to 0, and this value would go to 0. Anyone have any questions on that? You could also, let me think. So the current that comes through here, they have the same current, right? They're in series. So that current is never going to get here. Likewise, this current is never going to reach here. So, because it always goes the path of least resistance, so it'll follow here, and it'll never hit the other resistors. Any more questions before I erase this? So yeah, always use shortcuts when you can on the exam. Okay. So if you want to follow along, if you haven't already downloaded it or printed it out, go to ucfstudyunion.wordpress.com, click the Engineering tab, and then it'll be under my name, Rubba A. There'll be a practice exam if you want to follow. And I made a formula sheet too, if you don't want to make one on your own. And IO is here. So this one wants you to find the Thevenin and P average max delivered to ZL. So this is a phasors problem, and notice that they give you your voltage. They give you all your elements. They're already in the phasor domain. You don't see any cosine, nothing function of t. It's already in the phasor domain for you. And also notice that this is VRMS, so they've already converted it. They took the voltage and they divided by √2, so that's already included in that VRMS value. So when you're solving for power, you don't need to worry about, or when you're solving for IRMS, you don't need to worry about putting the √2 under that, because it's already included. Any questions about this circuit before I start? Okay, so the first thing we want to do, let's just combine these into one. So we'll get, that's just 25 plus J10. And then what method, oh, sorry, remember that to find Thevenin, there's several steps you could take. You could either find V open first, if you remember, V Thevenin, or you could short it and find I short circuit. Or if you want to go straight to finding the Z equivalents, which you're going to need for ZL, you can deactivate this, put a test source on here, and then solve for VT over IT. Or you can leave this on and then solve for Z equivalents with the V Thevenin over ISC. But we're just going to start off with V Thevenin because it's already open. And that ZL is an attached load, just like RL back in chapter 4. So we open that up, and now, right, this is in series. And we know this voltage. So what method? I know you guys always want to go straight to mesh, but should we use no voltage method on this? Yes. So we just have one unknown. V Thevenin's an unknown, but if you find VT, V, you should be able to, you'll know the current here, so it'll be fine. So V, and then I'll make my ground here. So that's 0 volts everywhere. And now this is 100. So this is in polar form, but you see there's 0 degrees, so it's just 100 VRMS rectangular. So I already just converted that right away. And notice there's this IO, and it's dependent. It's part of this dependent source. So let's go ahead and represent IO first. So IO is going this way. So it's going to be this node voltage minus this node voltage over the equivalent impedance. So what is that? 100 minus V over just that whole thing plus 10J. Any questions on that? So what's V? So actually, we're basically going to be solving for 5IO here, or yeah, 5IP. So everything's should be in terms of I phi, and we'll find I phi directly. So after that, we want to do a node voltage, and you always want to you don't want to do one here because we already know the voltage here. So we want to do it at the unknown. So we'll do a KCL here, and I'm going to assume everything going down. But notice that it's a KCL, right? I have no way of representing this. Yeah?
Sorry. So could we not solve for IO right there since we can plug that into a V? Just get IO.
Oh, yeah. Huh. Yeah, we can. Because if you see, we can't do a no voltage here. It'd kind of be a really tricky supernode right here because you can't represent this current. But as you see, because of this relationship, right away you can solve for IO, and IO ends up being, where is it on here? Oh, 3, so you simplify it, 100 over 30 plus 10J equals 3 minus J. And that's going to be in, ARMS. Remember when I said it's already in VRMS, so this is going to be in ARMS. Does anyone want me to go over the conjugate math for that? I usually plug it in my calculator, and I can show you after if you want to know how to do that. But I can go over the conjugate math. Is there anyone that wants me to go over the math for that? No? You guys good? Huh? Yeah? I'll just show you, I won't go through the whole steps, but basically what you do is you want to multiply by the conjugate, right? So you would just multiply by 25 minus 10J, because this is just basically 1. So you're able to just multiply it out, and then I'll cancel the J in the denominator, and you're able to get to this right here. Okay. Other than that, so we found IO. How does that help us? We know this voltage now, and we still need to know V Thevenin. So we could do another Ohm's law current. So this current right here is, I'll call it Ix. So Ix equals 5IO, which is 3 minus J, over, sorry, minus V Thevenin over 1. Now, let me see. But look, that's 2 unknowns. So I would just include, let me think. Oh, sorry, this is a voltage division. Do you guys see the voltage division on that? You've got a voltage right here. These 2 impedances are in series. And since they're in ohms, you could do a voltage division on them because V equals ZI, similar to V equals IR. So this would be our source voltage. This is the one we're interested in, this branch. And then these 2 added. So that's going to be so VTH will equal 5IO, which is 3 minus J, times the impedance that you're looking at, so J3, over the sum of the 2. And that'll actually give you 15 volts. Does everyone see the voltage division I did? Any questions so far? Okay. So I'm going to go ahead and erase this. It's recorded online, so if you need to go back and like see the, I'm just going to erase this part. Okay. So we found V Thevenin. So now what do we do? Should we go solve for ZL right away, or should we solve for I short circuit? Test source? That actually takes, trust me, it takes a lot longer. Yeah. So anytime you're using I short circuit, you're going to end up shorting something out, which will remove a component, right, from the, I'll show you right now. And also note that because we were able to use this side solely to find IO, IO is going to remain the same when we do this next problem. So we're going to short this. You guys remember this from beginning of the semester? ISC, it goes down because this is terminal A and B. And we want to find this current. And a short has 0 volts across it. And it's in parallel with this. And even if you did a KVL, you'll see this voltage equals 0. So that means this goes away because if it has 0 voltage, but it has an impedance, then 0 divided by Z will give you 0 amps as well. So this is also an open. That goes away. And IO actually remains here. Oops. You'll see that you can represent IO as 100 minus 5IO over this once again, and you'll get IO equals, 3 minus J amps RMS. So now how would I find ISC? It's, let's see, we know this current. We don't know this current. This current?
Oh, no, it's 0.
This current's 0?
That's a voltage.
It's not 0, but we know the voltage because this current, we know this current, so we know this voltage. Is this voltage in parallel with this resistor? Yeah, so we know the voltage of this resistor is also 5IO. So we can use Ohm's law to find ISC. So ISC will equal 5IO, which is 3 minus J, over 1 ohm. And then that's going to be 15 minus 5J. And that's also RMS. Let's see how like going the I short circuit route would have been is a lot faster than if we had attached a new source, shut this off, and then tried to find a ratio of VT over IT. Question.
What does I sub x represent exactly?
I sub what?
I sub x.
This one?
Yeah.
This was in the last problem. It was the current running through the 1 ohm, and there was a resistor here, or there was a inductor here. Yeah, so that was just an equation for one of the currents, but we didn't go through with it because it had two unknowns. So it was kind of like a node voltage method, kind of. Yeah.
So we didn't use it at all.
We didn't end up using it, right?
So what was that shortcut there that gave us the V Thevenin when we found that I sub x? Because there was two unknowns with the I sub x.
Oh, voltage division. So that voltage had two resistors in series,
Nice.
so it's split up. Yeah. Okay. Any other questions?
Why does it VTH on 15 volts RMS?
Why is it not, or why is it?
Why isn't it?
Why isn't it?
Yeah.
It is. I just forgot. Sorry. My bad. Oh. Okay. Any other questions? Okay. So we found ISC. We found V Thevenin. Remember, it's not just resistors, so I represent it as a box. This is going to be your Z Thevenin. And we got for our V Thevenin, we got 15 volts VRMS. So how do we get Z Thevenin? Ohm's law. So remember that, recall V Thevenin equals Z Thevenin times ISC. And we have ISC. So V Thevenin divided by ISC gives me that. So 15 divided by 15 minus 5J will end up giving us, where do I write this? I'm going to erase this blue stuff. So Z Thevenin equals 0.9 plus 3J ohms. Everyone cool with that? Oh wait, sorry, this is 0.3. Any questions on that? Nope. So we found Thevenin, and now it asks to find our average power, our max average power, delivered to ZL. So will our average power have any complex numbers in it? No, right? That's reactive power. So what's our ZL? So let me go back, and we're going to attach the load here. We go back, and that's when we bring back ZL. Because I had that arrow, we took it out, solved for stuff, and then we bring it back. What is ZL going to equal to? The conjugate of that. So back in chapter 4, our L would just equal our Thevenin, but with complex numbers, it's going to equal the conjugate, which is basically just the opposite coefficient of the complex. So we don't make this negative, we just make the complex number negative. So 0.9 minus 0.3 J ohms. Questions on that? Yeah.
So what's the difference between maximum power and reactive power?
Maximum power is, oh wait, no, so P average max, so they want to know the maximum of the average power, not the maximum of the, you can have like P reactive max or P average max. So average is just the real component of your power, and then reactive is the imaginary component of your power. So in this case, they want to know the real wattage, because it's going to be in terms of watts, not bars, for this question. Any other questions? All right, I'm going to erase this stuff. Mute it. Okay, so finding P max. So we're not finding average yet. We're finding just P max overall. It can have imaginary numbers in it. That's fine. So we have two impedances in series with each other, in series with a voltage source. And can everyone recall how to find power for, It's similar to resistors. How would you find power to impedance? There's like 3 different formulas. Sorry, what? VI. You could do VI. You do I squared times R, and you could do V squared over R. So we'll just do V squared over R. Oops. Well, in this case, it'd be Z. And I'm going to call this V. So what's V? Now, see, 15, when it gets here, it'll be lower than 15. It'll dissipate over this. We want the voltage across here, and you got 2 impedances in series with a voltage source. So you could do voltage division, right? So 15 is your source times ZL over those 2 added. And that's going to be your, there's like no room. And this whole thing is going to be squared. This whole thing represents V. Does everyone see the voltage division I just did? And then all that over ZL. So right, you plug in this for ZL, and you plug in this for Z Thevenin, and you're actually going to end up getting, let's see, for the voltage you'll get 7.5 minus 2.5 J squared over ZL, which is 0.9 minus 0.3 J. And that's going to give you 62.5 minus 208 J. Everyone good with that? So now this is P max, but we want the average maximum power. So what's the average maximum power here? 62.5, right? So this here is your real component, so it's your average. And that's going to be in terms of watts. So our answer for that is 62.5 watts. And if they ask for your maximum reactive power, that would just be your 208 in VARs. Any questions on that? So it's very similar to Thevenin with just resistors, except you have a conjugate that you have to take into account, and also whether or not the question's asking you for just average or the whole thing. So if it asked for a parent, what would a parent be, a parent power? It would just be the whole thing, right, in terms of volt amps. So this is actually, this whole thing is, if you do the magnitude of that, that'll give you apparent power in volt amps, in case they ask that. We'll go over apparent power in the next problem as well. I think, yeah. Any other questions? No? Can everyone see, by the way? Should I write bigger? Can you guys see? Yeah. Can I erase this? And then, okay. Oops. Okay, so this is another average power, reactive power, apparent power. Like I said, I don't expect there to be that much emphasis on this. So here VG equals 40 cosine 10 to the 6th T volts. And the question's asking for average reactive and apparent power supplied by the voltage source. So notice this time things are not converted for us. Everything right now is in the time frequency domain. And what's our frequency here? 10 to the 6th. And that's radians per second. So now we want to convert all these. So this one's already in Z. You want to get this and this. So ZL is JWL. That's how you convert it. And then ZC of a capacitor is 1 over JWC. Or likewise, you could bring the J up top, put a negative J over WC. So this ends up being 10 to the 6th times 80 times 10 to the negative 6. So J 10 to the 6th. So don't forget your units. That's negative 6. And that'll actually give you, this will be 80 J ohm. And for ZC, it is 1 over J 10 to the 6th times 25 times 10 to the negative 9. Okay. And that'll give you negative 40 J. Okay. And what about our VG? So this is in the form of, let's see, C, so hold on. C cosine WT plus theta. It's that form. So you want to convert it into polar, which is C angle theta. And then C is going to be 40, and your angle is just 0. There's no angle in there. So this is going to be in terms of V. And now this one's not converted to us in VRMS. And because we're interested in power, we're just going to go ahead and divide that by root 2. So now we'll get 20 root 2 VRMS. Yeah. Any questions on that? So Vm over root 2 equals VRMS. And your magnitude is, because this cosine only goes up to 1, so the magnitude is going to be 40. You want to divide by root 2, because when you're dividing for power, you want to find, RMS means like average real power, I believe. So they just want you to convert that when you're finding any power. In the last problem, it was already given to us in VRMS. So here we want to bring it, and then you just divide it by root 2. Yeah, there's like a proof for why you do root 2, but let's see. So yeah, I think we've got everything converted, and now we want to find the power of this. So I think the best thing to do, if we're just focusing on this, we can just combine everything down. Yeah. This one? Oh. So to convert an inductor to ohms, the equation is ZL equals JWL. And our W is 10 to the 6th. Because see this form, WT is the coefficient of T. Yeah. And then I did that for ZC is 1 over JWC as well. I just plugged them in, and this is 10 to the negative 9, and that's 10 to the negative 6. So we're going to combine these all down. Series, current doesn't split. They have the same current. You just add them because they're all in ohms. And then what about these two? Parallel? And this is 20 root 2. This is already in rectangular because it was 0 degrees. So in rectangular, it's just 20 root 2. VRMS. And then this will be 20 minus 20j. Because you're going to do parallel the same way. It's 40 times this over 40 plus this. And then this is going to be 80j plus 60. Both in ohms. So for this, we want to find power. So what's the only equation to find power at a source? It's just P equals VI, right? But in this case, P equals ZI. So that's the equation we're going to use. P equals ZI. Oh, wait, do I have that wrong? Sorry, P equals VI, my bad. It is still P equals VI. VRMS and IRMS. So how do I find, so we need this current, right? Because this current times this voltage will give us our power. So we can combine this one more time. And this will actually end up being, oh, it flips. Yeah. So this will be, I'm just going to add these two. $80 plus 60, oops, 60j ohm. Good? Anyone have any questions so far? No? So now I is just, we'll call this IRMS. Just Ohm's law, right? These are just in parallel. Voltage over impedance. So 20 root 2 over 80 plus 60 j ohm will equal IRMS. And that ends up being it's a weird number, 0.226 minus 0.169 j, amp RMS. So we now have the current, and we have the voltage. I'm going to erase this. So now, notice IRMS is hitting the negative, because we drew it that way. You could have likewise drawn it this way, and then you would have actually come up with a negative, the negative of this, because then it would be going, when you're doing the Ohm's law, it would be going through this terminal. So you'd get the negative either way. So P equals V, so the negative of that. V is 20 root 2 times the IRMS that we got right here. So this value. And this will give you, let me see, negative 6.4 minus 4.8 j. Now, actually, let me note something real quick. This IRMS, you want to do the conjugate of it for when you're multiplying it. Did you guys go over that, where you have to do the conjugate of I? No? Okay. So I'm going to erase those. Okay. So there's like several equations. So basically S, which is your apparent power, equals VRMS, IRMS, angle theta V minus theta I. There's like a bunch of ways to represent this, but this is one of the ways. And what happens is you'll have VRMS IRMS e to the j theta v minus theta I. And you see that negative term ends up giving you the VRMS e to the theta v j, and then IRMS. Oh my god, I'm writing upside down. That negative makes it the conjugate over here. Because that's what we're solving for. We're solving for S right now. So we need the conjugate. And it's represented by a star. So that's actually going to end up being, we'll just add a plus sign to that. And then that'll give you this value right here. So now, this is not, so now we want an average reactive apparent. So apparent power is the magnitude of that. Which will give you, I believe, where is it? Oh, that'll give you 8 bars. Not 8 bars, 8 volt amps. This is volt amps. That's apparent power. What is our reactive power? This one, right? The coefficient of the complex number. And it's 4.8 delivering, right? So I have no room. Right in here. So reactive equals 4.8 deliver. And then what about, oh, and that's going to be VARs, right? That's the unit for that. And then average. Just going to be the real component. So 6.4 watts. Watts. Do you have a question? 6.4 watts delivering because of the negative sign. I think that's pretty much it. Any questions on that? Yeah.
Just in general, for any problem. So when we have to label our components, like with the positive and negative terminals, like for example, the illustration on the bottom, like you,
Yeah.
So what if you labeled it, say, negative and then positive like that? I mean, I feel like I get tripped up a lot just because I can't assign proper signage.
Yeah. So I assigned the plus minus because I knew it wasn't directly in parallel with that. So it's going to be the same voltage. But if you did just wanted to assign minus plus, this would be negative. The voltage across here would be negative 20 root 2. If you flip the signs, because they're in parallel. They're supposed to have the same voltage, and it can't have it unless they're showing the same polarity. Plus, plus, minus, minus. So you can assign it like that, but you have to remember to put a negative out front when you're doing your Ohm's law, because now it's gonna be a double negative actually, because now your IRMS that you're trying to solve for is going in the negative, and likewise the voltage over this is a negative, so it'll cancel out and become a positive, which is I think what we got, right? Going this way, yeah.
So if you have it going through a positive terminal, then you have to keep it. Then you have to keep the voltage as is. Kind of.
If you're going through, so if I had IRMS labeled going this way, it still would be a negative voltage in this case. But you wouldn't put another negative out front because it is entering the positive terminal. If that makes sense. Is that kind of, let me see.
I just want to make sure I'm.
Do you want me to solve for IRMS, like with this polarity?
I mean, if it helps, sure.
Yeah, we can try. So say I labeled it this way, and I kept my IRMS like this. Now the voltage across here is negative 20 root 2. So before it was just 20 root 2 across, right? Just of the impedance. And then it's also entering the negative, because Ohm's law follows passive sign convention, just like power. So it's going to be V equals I negative IZ. And your V, when you just plug it in, is negative 20 root 2. And then it's that negative out front. And then your I is just, we didn't solve for it yet. And the Z is just this, 80 plus 60, J.
And it's just going to result in the same value.
Yeah, it's going to result in the same thing. Well, there's a negative here when we solve it, but yeah. Any other questions on that problem? Sorry, this one? That's apparent power. And it's the units for that is volt amps. So that's apparent. It's not apparent that it's apparent, but okay. Any other questions? Yeah.
The formula you wrote over there, S equal to VRS, is that complex power formula?
This is like apparent, not the magnitude of apparent. It's like, I don't know the exact term for this, but it includes both the complex and the real component. It includes average and reactive, this S.
Kind of the same thing like voltage efficiency times current efficiency cosine of theta V minus.
Yeah, and this is just in polar form. So the other one is in frequency time, and this is converted. This is the converted version.
This one is
Yeah, and then I brought it down to the other polar form, and this is the rectangular form that I found over here, of that same. They're all the same. Any other questions? Are you sure you guys can see? Yeah. Okay. I'm gonna go to the next problem. Ooh. Okay. What's this? Okay. Okay, RL. Let's do an RL circuit. Now this one's going to be lengthy. So everything here is in terms of kiloohms, milliamps. This is an RL circuit, right? It's just got one inductor, and the question says find VL of t, IL of t, and IR of t. And you want to do this strategically because you don't want to, because that's a lot to solve for, right? You don't want to find the initial conditions of all of that when you can just use shortcuts. So IL of t, what's the equation that relates IL of t and VL of t? It's VL of t equals L DIL over dt. So we don't even have to worry about VL of t till the very end, because we can just derive whatever we get for IL of t and multiply it by L. So we're not going to even worry about initial conditions for this. And they'll all have the same tau, because tau is based off after the switch opens or closes at 0. So it's after 0. And after 0, this is closed. And all these components, the IL, VL, and IR, they're all connected. So they'll all have the same tau. If they were separate, they'll have different taus. So just note that. And if there was like another inductor here in series, you can just add them, and IL of 1 should equal IL of 2 if they have the same inductance. And also, let me write it here. I have a general form that I follow. So x of t equals x of infinity plus x of 0 plus minus x of infinity e to the negative t over tau. And this you can put current, you can put IR of t, IL of t, VL of t, anything. And that's kind of just a general form for any first order circuit. So now let's kind of set up what we want to look for. We don't want to just kind of like start the problem. So like I said, we don't want any of the initial conditions of the VL. We don't need those. What about IL? Current can't change instantaneously in an inductor. So your IL of 0 minus will equal your IL of 0 plus. And then we want to also find our IL of infinity. Because we'll use 0 plus and infinity, it's just to plug it in. What about IR? Do we want IR of 0 minus? Can IR of 0 minus change when it gets to IR of 0 plus? Yeah, so we don't want it. We just want to go straight to IR of 0 plus. And then IR of infinity. And we'll also likewise plug these two in here. And tau, what's tau? L over R? And the R is based on after t is 0. So in this case, whatever's connected in parallel to the inductor. And we'll get to that. So now we can start the problem. I always like to start off with t less than 0. Well, you should start with t less than 0. And that's when this is open. So we don't even care about this side. There is an IR of 0 minus, but it's going to change, so we don't worry about that. So and this, if this is 0 amps, then this is 0 amps. So there's no voltage or current or anything going on here. So this is also ignored. So really we're just left with that left-hand circuit. And it's connected to this source for a long time. So this inductor is going to short. So there's no voltage. VL of 0 minus is 0. But IL can still have a value. And then 10. And this one's pretty straightforward, right? So this is like the polarity you were saying. This one now is flipped, minus plus. So they're in parallel, so I'm going to assign minus plus. And that'll still give me a positive 20 volts. But I'm trying to find IL, and this IL is hitting the negative. So I still put a negative out front of the whole Ohm's law. And then 20 over V over R, so 20, positive 20, over 10 kiloohms. And that'll give you negative 2 milliamps, which it'll be the same over here, negative 2 milliamps. So any questions on that? Yeah.
So is it advisable to label the component that's the other component other than the voltage source opposite from that one?
Like if I made it plus minus?
Yeah. Is it advisable to do that?
You can, like I said, you can do that, but you're going to have to remember that now it's going to be negative 20. This is going to be positive out here, but this is going to be negative.
Because entering the negative terminal.
The IL? So if I made this positive, and I made this negative, IL would be entering the positive terminal now, right?
Yes.
But what's the voltage across here? Is it positive 20? It is? No, because, let me think. So plus minus, I'll call this 20. And then you're saying, sorry, this was minus plus. And you're saying V, and you want it labeled plus minus, right? So let's do a KVL. Plus 20 plus V equals 0, so V equals negative 20. So that means this would be a negative 20 and this would be plus if you reverted the sign. So it would always have that negative 2 milliamps if current was going this way. Can't avoid that. Just kind of just do a KVL to check exactly if you end up flipping the polarity. Any other questions? I'm going to erase this. Okay, so we're done with t less than 0. There's nothing else we need to find, right? It's just IL of 0 minus. Now IL of 0 plus and IR of 0 plus. So that's after the switch closes. So that arrow is saying at t equals 0, it moves this way, and it connects to the dot. So it hasn't been like that for a long time. It was an instantaneous change. So this is not short. and the 5 kilo ohms comes back. Actually, it's actually gonna be lengthy, so I'm just gonna close it up here, if you guys don't mind that. Okay. And we know that 0 plus, we already know the value of this, it's -2. And do we know anything else? No. So we want to find, basically all we need to find here is IR of 0 plus, which is over here. And you can see like the resistors are all isolated. There's not really any, I mean, maybe you could do like a source transformation here, and then just add up. No, they wouldn't be in parallel because it's 5 kilo ohm. There was really not much you can do other than mesh or node voltage method. And do you guys mind if I show you both ways, the node voltage method way and the mesh, and show you they'll equal the same, depending on which one you're more comfortable with. So we'll start off with mesh. Now, okay, so this is, we'll call that, what did I call it here, I1. We'll call this I2. And then we'll call this IR. Now, remember, do I have a question? No? Remember that mesh is KVL. So when you're doing a mesh, you want to make sure every component can be represented as a voltage. Can we represent VL of T here? If I did a KVL here, is there really any way other than just calling it VL? There's no Ohm's law, right? Yeah, we can't use this because we don't have the function of T. So we can't use that. But we know that this is -2, so we already know this branch anyway. We got 2 super meshes here, this one and this one. So you're going to do one big KVL around here. Do you guys see that? Any questions about that? No? Okay, so let's do the super mesh equations first. So IL is going down, and that's -2 milliamps. And I1 is going down, so it'll be positive. And then I2 is going the opposite direction, so minus I2. So we got 2 unknowns so far, one equation. And now this one, another super mesh. One milliamps going down. I2 is going the same direction. IR is going the opposite direction. Any questions on that? Okay. So now we could do, so we have 3 unknowns, 2 equations. We just need one more. So we're going to do this big KVL. So going this way, plus 20 volts, plus 10 kilo ohms times, only I1 is running through that branch, 0 is running through the other branch. So it's just I1. And then go all the way here, because that's just a short, plus 2 times IR. And then all the way here, plus 5. And then I2 is just I2, equals 0, because this is a KVL. Any questions on that KVL?
20 plus 20, is that the X different?
Oh, sorry, this is, where did that come from? I don't know what that is. It's blue. Everything in blue is our mesh equations. So we got I1, I2, IR. Those are our 3 unknowns, 3 equations. We need to, I'm going to set up a matrix. Just, I haven't set one up yet. We want to find I1, I2, and IR. For the first equation, coefficient of I1 is simply just 1, positive 1. Coefficient of I2, -1. There's no IR component, so that's just 0. And then the constant, it's already put on the equal side, and it's -2. And then our second equation, the coefficient of, there's no I1 component, so it's just 0. Coefficient of I2 is 1. Coefficient of IR is -1. And then the constant is 1 on the other side. Now for this one, Let's see. I'm just going to move the 20 over, and that's going to be negative 20. And then the coefficient of I1 is 10. And the coefficient of I2 is 5. And then the coefficient of IR is 2. If you haven't seen this before, don't worry. Basically, you plug this in your calculator. So this is matrix A. And you want to invert it and multiply it by matrix B. And B, I believe this is 2 by 1, and it's 3 by 3. 3 by 3 times inverted times the 2 by 3, or sorry, 3 by 1, 3 by 1. And that'll actually spit out the answers in order, so I1, I2, IR. And what you end up getting, let's see. Gotta just find my answer. They're essentially like really weird numbers. So IR ends up being negative 5 over 7, which is about negative 0.71 milliamps. And then, let's see, I1 ends up being negative 32 over 17, and I2 ends up being 2 over 17. That's a 2. So we don't even need these. We found IR directly, yeah.
Do you have to take into account the decimal place that the 2 milliamps, for example, the 2 milliamps goes to? Because like in the matrix,
Mm-hmm.
you have -2. Would you do 0.00?
No, because everything's in terms of kilo ohms. So that's already taken into account. The 10 to the third cancels out the 10 to the negative 3. So you end up getting the right values. These are all in milliamps. So, good question. Any other questions? No? So yeah, we basically found IR. IR 0 plus was negative 5 over 7 milliamps. Okay, so now we want to find the infinity circuit. So can I erase this stuff? Oh wait, you guys want to see node voltage method too, right? Yeah. Yeah, okay. Okay, so where am I going to put my ground? Any guesses? Should I put it here or here? Raise your hand if I should put it here. Raise your hand if I should put it here. All right, raise your hand if I should put it up here. All right, you guys just don't want it ground. No? Right here? Well, if I grounded this, would I know this voltage? Bottom right? I mean, honestly, you can ground anyway. So if I grounded here, I'd get 1 unknown, 2 unknown, 3 unknowns. I'd get 3 unknowns. If I grounded it here, I know this is negative 20, because node minus 0 entering the negative equals negative 20. So node equals negative 20. And then this is ground, and we'd get VA, 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 VB, because of this resistor. So it's actually unavoidable. You're going to get at least 2 unknowns. But I think the other way you got 3, I believe. Yeah. So this way we know this node right here. So, okay. I'm going to assume everything's going out. So this one's already labeled out. This one's labeled out. And then here, I'm going to assume this way. Okay. So we're going to do one big KCL at the node You do it at each homogeneous node. So here, this is all VA. So there's one big KCO. So everything's leaving. So here, the current is going to be VA minus 20. So VA minus 20 over 10. This one's already given. We already know it. It's -2. And then here, also given, plus 1. And then IR, we'll pretend like we don't know it yet. That's going to be IR. Equals 0. Everyone good on that KCL? So that's equation 1. Oh, sorry, IR, my bad. This is VA over 2. Oh no, VA minus VB. It's not 0 in this case. So VA minus VB over 2 equals 0. So 2 unknowns, 1 equation. We just need 1 more equation. And we'll do it right here. Because this is all homogeneously VB. So looking here, this one's going in, this one's going in, this one's leaving. So the 2 going in are 1 plus the IR. And I'm not assuming it going out. If I was assuming it going out here, it'd be VB minus VA over 2. But I kept the label. So it's still VA minus VB over 2. And it would be on the other side had I assumed it going out. And now this one's going out. And this is just VB minus 0 over 5. So VB over 5. We don't have to solve it through, but essentially now you have 2 equations, 2 unknowns, set up the matrix, you get the same answer.
Sorry, so you're just ignoring units because you're doing shorthand, right?
I'm ignoring units because this is in kiloohms and this is milliamps, so at the end, my answers will still be in volts.
Okay.
Yeah, but if I had ohms and milliamps or kiloohms and amps, then I'd have to do some tweaking. I usually just try and make sure everything's converted first and then start the problem. But you don't have to include, you can label kiloohms, but it's not going to change the answer. Yeah.
In order to find the tau, we have to change it to
The tau is different, yeah. And the tau you want to do 2 times 10 to the third. Like you have to get seconds. Yeah, because that's based on ohms for that one.
and then the tau in milliseconds.
I think, what is it, L over R? So yeah, it would be milliseconds if you kept it like that. As long as this was in henries. So if this is in millihenries, that's a different story. I think that would be microseconds. So yeah, I'm not going to go through and solve the math again, but this is how you would do the no voltage method. Any other questions on this? No. Okay, so we still have a lot to do. So now we don't know anything. And we're doing the infinity. So now at infinity, everything's connected to both sources. So this still shorts out, right? We don't need these. Okay. So this shorts out. Now notice this. This circuit, completely independent from this circuit. Because any current that comes here is just going to directly funnel through IL. And notice now, like this is B, and this is node A. These two aren't parallel, right? So if I want to find IL of infinity and IR of infinity, I know this current right away. What is this current? I'll call it I1. Sorry, what?
20 over 10K.
Positive 20 over 10K?
Negative 20.
Negative 20 over 10K. So negative 2 milliamps, again. This is kind of like the zero minus behavior. It's just isolated. So we know that. And then what about IL? We still can't find that yet. What about over here? This is a short, right? So this is B over here as well. And this is B. And we'll call this A. Do you guys see what these are connected in? They're in parallel. I don't know if you guys can visualize. Imagine if I'm going to just move this up a little, and I had 5 kilo ohm here in parallel with the 1 milliamp and the 2. You guys don't believe me? Okay. Let's see. So you agree this current is in parallel with this one. And just like this voltage was in parallel with this one, let's see. So this B, 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 A, B. So, yeah, exactly. And I'll just set up like this. Two, and then 1, and IR. So just like that last problem, IR is going down, but this source is going to naturally split up. So when you're doing the current division, you want to don't forget about the negative out front. So IR equals negative the source, 1 milliamp, times the, so we want this branch, so we put the opposite branch on top, and then you add them. So 5 plus 2. And I think that gives you, I don't think I actually have the, oops. Can someone do the math for that and let me know what it is? Is it negative 5 over 7? Yeah? Okay. I did have it, my bad. So it actually stays the same. And then, so we found that. So now we have to find IL of infinity, which is over here. So we know this current, we know this current. How can I find IL of infinity? Any mesh? You say mesh? That would take forever. Like you mean a mesh here, mesh here, mesh here? Let's see. I'd have, well, I know this is a known. This is a known. So I would have to do one mesh here. No, because see, you'll still need to know, this is like a super mesh here. We can't represent that in Ohm's law.
Couldn't I say that's just equal to the loops on the left and right side of it?
Oh, I1, but we don't know this one, right? Huh? Yeah, we could calculate with, would we just do another current division?
Yeah, exactly.
Yeah, so we would just do the opposite current division here to find, let's see, if this is going down, I'm going to make it go the right way, splits upwards, so it'll be positive. So this current, I'll call it IX. IX would equal 1 amp, positive 1 amp, 1 milliamp, my bad, times the opposite branch, 2, over those two combined, which is 7. And that gives you 2 over 7. Yeah. So now how do I find IL? So it's like mesh, but like you can think of it also as a KCL. That's what the super mesh is. It's basically a KCL. So this KCL, this one's entering, this one's leaving. So these two are entering, and this one's leaving. So I never have any room. Sorry, what? What's IX? 2 over 7. And that was just a current division. So now IL and IX are entering. So IL plus 2 over 7 will equal the IO1 leaving, which we got negative 2 up here. So IL of infinity will equal, where is it? Did someone, I think that's just negative 2 over 7? No, that's negative 16 over 7 milliamps. Any questions? All right, we're almost done with this problem, I promise. So now what do we have left to find? Yeah?
When the t equals to 0, can you say resistor current of 0 plus voltage current of 0 minus?
No, because the resistor is represented by Ohm's law, V equals IR. This can change instantaneously for the resistor. But notice here, the current is a derivative, can't change instantaneously. So IR, like in the other problem, or sorry, not in this problem, 0 minus was different than. It was like, it was just this, 2 times, it was 2 milliamps. Or yeah, negative 2 milliamps. So, no wait, my bad. They were in series, so this was just negative 1 milliamps, which is different than negative 5 over 7. So yeah, they can change instantaneously. Anything on a resistor, the voltage on a resistor and the current can differ. So you always just want to find 0 plus and infinity. It's only the inductor current that doesn't change, or the capacitor voltage. Any other questions? So what do we need? What's the last thing we need to find? Tau. And is that before 0 or after 0? After. So this comes back. And we basically want to open this up and find our equivalents. So what method, so right now, you can't really combine the resistors because there's sources in the way. So what method can I use? Starts with a D. Huh? Deactivation source. So you turn off a current, there's no current in an open, so it becomes an open. You turn off a voltage source, there's no voltage across a short, so the short's out. And when you're, so it looks like right now these are on series, but you're trying to find the R equivalents here in the middle. So you want to kind of look at it as like scrunching inwards. So these two are in series for sure. You just add them, that's 7. But the 10 and 7 aren't in series because you're trying to find the R equivalents in the middle. Now if I was trying to find it here, A and B, then yeah, they're in series. But in this case, move the 10, 7's here, they're in parallel. Do you guys see that? Because you want to find whatever's in parallel to your A and B. So 7 parallel 10, 70 over 17. All right, does anyone have questions on that? Do you guys see why they weren't in series? Yeah? So just remember, like on the exam, don't go straight to saying like, oh, these are on series. Kind of like start, what's it called? Equating them inwards like that. Or if like A and B were up here, you'd want to go up. All right, still not done. Tau is now going to be L, it's already in Henry's, so we don't have to convert it. And then R, which is 70 over 17 times 10 to the third. And that will give you a really large number. Or sorry, a very small number. So it's like 2.43 times 10 to the negative 4 seconds. So yeah, the answer for tau is 2.43 times 10 to the negative 4 seconds. And now last three steps, just plugging it into that equation. So let's do IL. IL of t will be x of infinity, which was, IL of infinity was negative 16 over 7. And then plus IL of 0 plus, which was negative 2. I'm using this equation up here. Minus x of infinity, which is negative 16 over 7. E to the negative t over that. So negative 1 over this gives you negative 4,115 t. And this is all in milliamps. Is everyone good with that answer? I just plugged in all these values. And if you simplify that, it's going to be, this is going to be 2 over 7. So now how do I find VL of t again? Derive, yeah, question? This? Like where did I get it from? Negative t over tau. Yeah. So the tau is this, so I just did negative 1 over this, and I simplified it to 4,000. Yeah, that's where that's coming from. I just simplified it. So now I want to derive this and multiply it by L. And that'll give me my VL of t. So my L was 1. And then times, this is going to be whatever the derivative is. Derivative of constant 0. Derivative of e, it's just itself, times the exponent. So negative 4,115 times 2 over 7, e to the negative 4,1115 t. And that's in volts. Any questions on that? No? Oh, yeah?
Oh, wait, you said it would be in volts. Oh, I mean, like, if it's the derivative of something that's in.
Why wouldn't it be in millivolts?
Why would it not be?
Let me think.
Just because it's the derivative. It's the derivative of terms of something that's in millivolts.
Trying to think. Well, because milliamps and kiloohms give you volts, and we were solving this problem with kiloohms, and our tau is in is from the kiloohms. So
The exponent should be dimensionless. The exponential function should
yeah, no, I see what you're saying. That's questionable. I don't know, to be honest. Now that I think about it, if it's millivolts or volts, look into it. I think some practice problem will have that, like from milliamps. Yeah, hopefully. That's a good question because I thought it was just volts, but we'll leave that question mark for now. And then what about IR of t? So I'm not going to go through that. IR of t, we're going to do the same thing. It's the same tau. You're going to plug in x of infinity, negative 5 over 7, plus negative 5 over 7, minus 5 over 7. So you just plug that in. Any other questions on that? The next one's even lengthier. It's RLC. So what time is it? Okay, let's speed things up. Okay, I'm gonna erase this. If I know I'm going like a little fast and kind of messy, but if you ever need to like look at, you can come see me after if you want to see like values. But that's kind of like the process you want to go to do when you're doing like RL or RC. Set it up and then go in order. Okay. Actually, this one's not too bad. It's just, it looks a little weird. Oh, wait. This is labeled for you, VC of T, and that's 1 farad.
If you were not sitting, doing this, helping us right now, how long would it take you to do these problems?
The math was pretty lengthy for it. I think this whole exam review, would take me about 2 hours probably, if it was like the first time looking at it. Yeah, it took me a while to figure something out because I made some of these up. So I had to that's why I got really weird numbers. I checked the answers though on like circuit simulators. So they're right, but yeah, it took about 2 hours. It was pretty lengthy. Especially that last one was, because I did both ways. I showed you both ways. So let's see. Okay. So this is RLC, right? So let's see, and the question asks, find VC of T. So right here. And I just kind of, they don't give you a labeling, but I'm just going to do IL, going down. And you can kind of pick. So you could also say it's going up. Just make sure when you're solving for VL, the IL is going in the plus terminal. So you can pick either one. It's just an assumption if it's not given. This one's given, VC of T. So IC goes this way. Question?
Okay, so make sure that the IL is going to the plus.
Yeah, if it's not labeled, if neither of them label VL or IL, you can pick as long as you make sure IL is going to the plus. Yeah. And let me just start writing out. The first thing I do with these problems, I just start writing out equations. So VL of T equals L DIL of T, and then IC of T equals C dVC over dt. And are there any other equations I'm missing? No. So with RLC, the first thing I do is find initial conditions. So I know that IL of 0 minus will equal IL of 0 plus, and that VC of 0 minus will equal VC of 0 plus. And we need these initial conditions because when you're solving for your coefficients, A1 or B1 and stuff, you're going to need these values, the 0 plus values. Or if it's step response. So let's look at this real quick, actually. So it's closed for a long time, and then it opens. But even when it opens, these two are still connected to a source. So this is actually going to be a step response where you add a V final or V infinity at the end of your equation. So if if it disconnected for a long time and there's no sources, it would just go natural response. You wouldn't add that V of infinity because everything would go to 0. Okay, so initial conditions. So this is closed for a long time. So this opens, I'll just redraw it. And also, I just put this in there just to show you that if you did get two sources in series, you could just add them. It's like a KVL. So +5 + 5. So that'll just be 10 with the same polarity. And this shorts out. And this opens. So now, let's see, we have, how did I solve this? We can do mesh on this, yeah.
So this might be an obvious question, I'm not sure. So is this a parallel?
No,
No, it's not.
no. We'll get to that. We'll get to what kind of circuit it is for this. Because it's always based on after time is 0. So however it's connected. And I'll show you how to, because there's sources in the way, and I'll show you how to see it. So this is 2, 10 volt. This is 20 ohm. And this is 5 ohm. And yeah, we'll just do a mesh because we already know one of the meshes. This is 2. So we just want to know IL, and IL will have it going this way. So let's do a KVL. So 5 times IL plus 10 plus 20 times, so IL minus 2 equals 0. So you can find IL right away. IL ends up being 1.2, and that's amps. And so we know that one. Done with that. Any questions on that mesh? No? And then what about VC? So we know IL now. IL goes through the negative terminal. This is in series. So your VC is going to be the negative of that, and just Ohm's law. So IL times 5. So IL is 1.2 times 5, and that'll give you -6 volts. Yeah, that's -6, right? Yeah. Sorry, I'm writing diagonally. Okay, so we found that. Any questions on how we got our initial conditions? No? Okay. So the next part of the problem is this opens up. And we're just going to go straight to the infinity part. So this opens up. This goes away. There's no current. These don't short or open because we're looking right now at the function of t. So we want to keep these in play. And now we need to figure out if this is series or parallel. All you do for that is you deactivate all the independent sources. So this shorts. And this opens. So I think it's now pretty apparent what kind of circuit it is. Series? Yeah.
What's this for?
What I just did?
Yeah.
I deactivated all the independent sources so that I could figure out whether it's series or parallel connection. And when I did that, I see they're all connected in series. So now it just becomes a pretty simple series RLC. So the only difference between the series and parallel is the alpha. So for alpha in series, I think that is R over 2L. And as you notice, that 5 doesn't come to play, so R is just 20 over 2 times 2 henries. And that's going to be in terms of radians per second. So 5 rad. Cool. And then W naught's going to be the same for both. W naught's going to equal 1 over root LC, which gives you root 2 over 2. Root 2 over 2 is about 0.71. Oh, hey.
So you're saying that if we can't already tell, like when we first get it, if it's series or parallel, we can always use deactivation to
Yeah, just not with a dependent source. Yeah. Normally, even if you do have a dependent source, you could probably do like a super mesh or a super node. And so a super node would mean everything can be represented in one KCL, so it'd be parallel. Super mesh would be one KVL, which would be series, if you had a dependent source, because there are problems like that. And yeah, so alpha is bigger, right? So alpha is greater than W naught, and that is overdamped. And so our equation will be, remember this is step response because it's still connected to those sources, plus A1 e to the S1t plus A2 e to the S2t volts. Everyone good on this equation? You guys seen this before? It might maybe like has V of F, but it's the same thing, or like B1, B2. And then you're also gonna, to find A1 and A2, you're gonna need VC of 0 plus, which is gonna be VC of infinity plus A1 plus A2. And then you're gonna wanna also have VC of 0 plus over dt, which is A1 S1 plus A2 S2. And all this stuff, there's a good summary at the back of chapter 8 in the Nielsen-Riedel textbook that kind of just labels it all, and you should just have that on your formula sheet. And S1 and S2, they're just going to be, that's also like a given, negative alpha plus minus root alpha squared. Is it plus? It's plus, right? Minus? Minus W naught squared. So you know your S1 and S2 already because you know your alpha and W naught. So the only things now you really need to solve for are A1 and A2, and then plug it all in. So we found VC of 0 plus, negative 6. Let's see. And then did we find our dVC of 0 plus? No, right? So I erased the thing. Let's see. I'm going to redraw this. So if you notice, actually no, sorry, this goes away. So IL's like this, and we want to find VC of 0 plus dt. So notice this equation. IC of 0 plus equals C dVC of 0 plus over dt. So therefore, yeah, so we just want to find IC of 0 plus. We find IC, that was this way. And notice it's just the opposite of what we find for IL, which is 1.2. So IC of 0 plus will be negative 1.2. Yeah, so negative 1.2 over C, which was 1 farad. Yeah. Anyone have questions on that? Okay. And S1, just for reference, I won't solve it out, but S1 is negative 0.05, and S2 is negative 10. So now, there's one more thing we have to find. V final. So this becomes a short, and this becomes an open. So we know that this is just 0 amps, and VC of infinity is here. There's still voltage here. There's no current, but there's still voltage, so don't forget about this. It's not just whatever voltage is over the 20 ohm, 2 amps. But there is no current here, so this 20 ohms is directly, I'm going to leave it like this. So this is going to be 40 volts. And then I could do a KVO, right? So going this way, minus VC, plus 10, minus 40, equals 0. So VC equals negative 30. Good. And then, yeah, we found that's our VC of infinity. 0. Oh, sorry, not 0, negative 30. And, I mean, I'm not going to, now you just plug it all in and you just solve for it, because now you have 2 equations, 2 unknowns, A1, A2. And if you want to check at home, it's going to be your A1 is going to equal 24, and your A2 is going to end up being 0. And then you would plug in A1 and A2 to this. There's no tau in this. An S1 and S2, you'd plug that in. You'd plug in the negative 30 volts, and you'd get your VC of t without having to use differential equations. Any questions? No? And if the problem was like, find IC of t as well, derive it, multiply it by c. Okay. So I've got 20 minutes left. For the people that are in chance class, I'm about to go over an op-amp question, but I'm using like node voltage method for it. So if you want to kind of look at what that is, that's going to be my last question. And if I have time, I could go over maybe one of Chan's final exam questions. Let me just find the. So any questions on this? No? Like I said, I know this is like super messy, but it's recorded online if you needed to kind of look back at the values or just come see me after. I've got slightly cleaner solutions. Okay. So if you're not in Bahal's class, this is a prereq for networks and systems. It's actually, like, it's really straightforward, like, once I explain it. But any other, is there anything I didn't go over that you guys wanted me to go over, topic-wise? I don't think anyone's getting superposition, right? Unless you're in, is anyone here in Fahim's class? Okay, you guys are getting, and you guys are doing filters too? Talking about principles? Okay, so that's principles of EE. They don't cover an EEL, so I don't go over that. But I am going, you guys have op-amps, right? So I'm about to do an op-amp question. Thanks for showing up, and before you leave, make sure that you go online and scan the barcode and take the survey. Let me see. 2, 3, 6. Okay, yeah, just make sure you take that survey. They need to see that people are showing up to these things. And yeah, good luck on your final. So were you able to find the schedule? So if you go on UCF Study Union .wordpress.com, that first page will have a link to the schedule. And you can click the electrical networks, and it'll lead you to my the YouTube page. Also, if you were able to access my review, there's a link that says live stream here. You can click that, and it'll take you to the YouTube directly. So either way, that's how you can get to it. You're welcome. All right. So this one, find IA. I don't know if anyone has the thing printed, but I think I wrote everything. And it says like 6 volts, -6 right here. You can just ignore that. That's kind of just your constraint. So it's saying if you get an output value right here, output voltages that are larger or smaller than 6 and -6, you probably want to check your work on that. But you can kind of just ignore that. Okay. So how should I start this problem? Well, first, this is millivolts. I'm just going to change that right away because that's in volts. 10 to the -3 volts. How do you guys think I should start this? Node? Yeah, oh, I should first mention, just a reminder, I minus equals I plus, which equals 0. And then V plus will equal V minus, which equals, yeah, for an ideal op amp. That's always the case. So this is 0 volts, so V plus here is 0. So up here is 0. Likewise, ground 0. So therefore this is 0. And there's no current, so this is kind of open. There's no current, that's open. And so you said label for node voltage. So let's see, we know this is 1 volt. We know this is 0. We can call this V1, V2. Likewise, this is 0, so this is 0. This is 150. And then, yeah, and then I'll label, so these are in series, right? And this is in series. So this is all one current. And I'll call that I2. And this is all one current. That's I1. And to find IA is going to end up being voltage 2 minus voltage 1 over 1K. So we need to figure out V2 and V1, and we'll find IA. So let's do a KCL right here. So we know this is 0, but we can't do a KCL right here because there is a current here, and it's going to be impossible to figure out. So we can do a KCL here. So I1, right, equals I1 because it's the same current. So this current is 1 minus 0 over 10 kilo ohm. And then this, it's equal to this current, same current, 0 minus V1 over 47. And then you'll end up getting V1 equals looking for it, negative 4.7. If you solve, because it's one equation, one unknown. Likewise, over here, you're going to do the same exact thing. I2 equals I2. So this I2 will be 150 times 10 to the negative 3 minus 0 over 33 equals the same current, 0 minus V2 over 220. And that's also one equation, one unknown. So V2, you'll end up getting, looking for it. Did anyone do the math for this? Oh, 1 volt. And I'm getting 1 volt. Okay, cool. So now we have V2, V1, and like I said, we set up this equation. So IA will just equal V2, which is 1, minus 4.7. It's negative 4.7 over 1, and then that means IA equals positive 5.7 milliamps. Any questions on that? No. So this was just asking for IA, but sometimes she'll do something like that. So now you have to find R, but she gives you IA. You would do the exact same process for that. It'd be a no voltage method. Yeah, question?
With the filter voltage source change your equation though?
Oh, yeah, my bad. The rest is right because I have it written down, but I forgot to, yeah, this is negative. Good catch. So it's negative. But because this is negative and this is negative, it still ends up being the positive. I just forgot to write that. Yeah. Any other questions on this? It's 2 op amps, but it wasn't too bad. If you notice. Other than that, is there any topics that you want me to cover? Yeah. Superposition? Are you in Bahal's class? Did he say that he was going to give you a superposition where they have 2 different W's? Yeah, 2 different frequencies.
We haven't gotten that far with phasers.
If you got like a question and you had 2 sources, but they both had different W's, that's when you would use superposition for phasor stuff. Other than that, I can, because I have 8 minutes, but I can kind of just briefly. Yeah. I mean, just like the concept real quick.
So it's just basically taking an element out and then evaluating it and then replacing it.
Yeah, so